You don't need sound, you had this in practice.
I love that.
Okay.
I can hear something.
Can you hear me?
Yay, sound. So people can hear you, I think.
Yeah, people can hear
It's
me.
really delayed.
It's the sound from like 10 seconds ago.
10 seconds ago. Okay, it should work. Hello everyone. I hope you're excited for this. I don't think so, but first I would like to say, if you did not like the course so far, just complain about it in the course evaluation, because otherwise people in the DPC can't do shit about it for next year. And I think you wanted people last year to do that as well for you, so do it for the people next year. As for now, we're going to some of the topics of tonight. Namely, first we're going to talk about limits, then we're going to talk about some asymptotics, sequences, then we're going over to functions, and with the last two parts, with derivations and with the integration, I'll give it to Daphne, who will explain the other two parts. If there are any questions, you can ask them in the chat, you can ask them on Discord. There are people in the chat that will read that and forward the questions towards us if it is needed. Everything still good?
Yeah, okay.
Yeah? Okay. Then we can go. So first what we're going to talk about a little bit is limits. And limits is just when you have a simple function that is dependent on n, when you are making that n very big. For example, if you have a limit of 1 divided by n, if n gets bigger and bigger and bigger, of course that will tend to 0 because you're dividing by a bigger and bigger number. While 1 over n is of course very easy to solve and see that of course will go to 0, you can have more difficult limits like the one below. So if we're going to solve that one, let's write it down here. D is, oh wait, I don't know what's going wrong. Let me just,
I saw something on there.
yeah, I know, but the mapping is going wrong.
Ah, okay. Someone says dark mode paint lit.
Yes, of course, it's very lit. Okay. This right now. No, still not. It is because force. Okay, now we should have it. No, still not. We're getting closer and closer. I have to do this by hand quickly. How big actually is the resolution? Ah, see, that's the problem. Okay.
I love all those.
Are the comments shitty?
No, they're getting closer to the limit, question mark.
Yes, it's definitely getting closer. One day we'll find the answer. And who knows, maybe it will be 42. Yeah, there we go. We have 1. Technology 0, humans 1. Okay. So, what was the, let's go back to the, so we want to take the limit of n squared 3n minus 1. So the limit of n to infinity of n squared plus 3n minus 1 divided by 8n squared, it's a very big 2, n squared plus 3n minus 1 over n to the power 3. Think this is correct? Yes. Okay. So if you have a bigger limit like this, and right now we want to know if these limits go maybe to infinity, to 0, or to something else. What we want to do is to check in this limit which n has the biggest power, which has the most influence. Because if we fill in for n, for example, 10, if we have an n squared, that will be of course 100, while 3 times n will be 30. And if you have an n that's bigger and bigger and bigger, the n squared will of course have more and more impact. So how can we write down that that will have more and more impact? Well, we see what the biggest power is with n, and in this case it's 2, as we see right there. What we will do right now is divide by this power. So every element in our fraction we will divide by n squared. So this will be the limit of n going to infinity of n squared divided by n squared will be 1. 3n divided by n squared will be 3 divided by n. And if we divide 1 by n squared, of course, that will be 1 divided by n squared. For the last one, of course, we have 8n squared divided by n squared, which will be 8. Then, of course, we have 3n divided by n squared will be 3n. Minus, well, we already have divided by 1 over n to the power 3, so this will be 1 of n to the power 5. Now, if we know that the n in the denominator is bigger than what is in the numerator, and in this case we only have an n term inside the denominator, we know that all these denominators will turn to 0. So if we fill in n very big, what will happen actually is 1 will stay 1, 3 divided by n will simply converge to 0, 1 divided by n squared will also converge to 0, 8 will stay 8 of course, not under influence of n, this will converge to 0, and the last one will also converge to 0. So in the end we are left with 1 over 8. And that's how we calculated this limit. So if your n is going to infinity, find your biggest power, divide every term by that power, and then calculate the answer if you fill n very big in everywhere. If there are any questions, you will let me know, right?
Yes.
Okay.
Just a remark, your face cam is over the text on the
So your
top
face cam
left.
is in the left corner.
So in this case,
Ah,
it's
I don't see my own face cam. That's the problem.
No, that's fine. Just no, it's like only over the limit text. So
Okay. I'll just
Oh, Arjan,
yeah.
do you have to write the in-between steps, or can you just jump to 1 over 8?
So the thing is, also with the exam, if you write down the answer immediately, we do not know if you maybe guessed it right or like how you got to that answer. So maybe you saw it with a neighbor or maybe something else happened, but showing these steps is like convincing the teacher that you understand this topic. So I would advise you to have like maybe the step that I wrote down in between. You can have more steps. It's just that you know for certain that the number of steps that you write down convince the person that is grading that you know what you are doing. So I would advise to have like some steps in between that are like logical, not too big steps. Yes? Okay.
I think so.
Then we're also going to talk about asymptotics after these limits. And asymptotics look very much like limits. The thing is that with these asymptotics we're looking at a specific value. So before this with limits we were talking about taking n to infinity. And right now we're taking x, for example, to 0 or x to any other value that is specified. And then we can talk about these asymptotic relations when they both are like behaving in the same way when approaching that point. So in Word, that is that the limit from x to 0, for example, from f of x divided by g of x is 1, and then you can write it down as f of x with a nice tilde in between to g of x. So again, in an example, when we are going to take the number 0 and approach it with these two functions, we're going to take the limit of x to 0 from x to the power, my memory is not that good, 5 plus x to the power of 3x to the power 3 divided by 3x to the power of 5 plus x to the power 3. I hope the flashing is not annoying many people. So if we are doing this and going towards a point, what we are doing is actually not looking at the biggest power, but looking at the smallest power and trying to divide by that. Because right now we are trying to fill in 0. If you fill in 0 in this limit, you get like 0 plus 0 divided by 0 plus 0, which is 0 divided by 0, which is not really defined. So we cannot do that. However, this has a value. And what we do is we're looking for the smallest powers. Instead of the largest, we look for the smallest. And then we divide everything by the smallest power. So let's do that. If we have the limit of x to 0, x to the power 5, the smallest x to the power 3, so we'll divide by that. So we're left with x to the power of 2 plus 3 divided by 3x squared plus 1. Now, when we fill in 0 here, now we can, because if we fill 0 in, we get 0 squared, which is 0, plus 3, divided by 3 times 0 squared, which is not 3, it's 0, plus 1. So the final answer for this limit is 3. Yeah? Now, this is how you solve these asymptotics when you have functions and you are approaching a specific point. There are some simple, some standard asymptotic relations that you can memorize, because that's not a cheat sheet allowed with the teacher. Crazy person, I know. I've listed them here. They are also in the lecture. I think the first lecture or second, or no, practical. I think the second practical. Yeah. They are listed there as well, so you can check them out, but it's good to know these, because what this means is if you have a limit which has one of these functions, for example, you have e to the power of x minus 1 divided by x, and you take the limit of it, you can replace e to the power of x minus 1 with x, because they converge to the same function at that point.
Arjan, could I say something? Like only for x going to 0, right?
Yeah. And so these asymptotic relations are for x going to 0, indeed, yes. Okay. If not any...
yeah, there's some questions. So
yeah.
What if you do not have the same powers in the fraction? So if you cannot get two numbers?
So if there is not... so the fractions are not the same. If they are in the denominator, then you probably have a problem, because you cannot fill in 0 anywhere, because you will divide by 0 or you will divide by 0 in the numerator. So if you're, for example, with the last one, right now we had x to the power 3 there, like in the numerator and denominator. If this was not a 3, if this was, for example, a 2, then when we divide everything by x to the power 2, then it would be okay, because then we would have 0 divided by 1, and that will be 0 if you follow the same steps. However, if we are doing, if this was not a 2, but if this was a 4, then we divide everything by x to the power 3. So in the denominator, we are left with x, 3x squared plus x, and if we fill in 0 here, we will always divide by 0, which will always give a problem. And if we divide by something bigger, like for example x to the power 4, then we'll have 3x plus 1, and then we will have x plus 3 divided by x, and then this will be a problem, because this will be 3 divided by 0, which is impossible. So in that sense, you would have a problem. So if the denominator powers are bigger, you have a problem. If not, you will probably end up with 0, but that's not always given. But you can still have an answer, yes.
Okay, and could you also say that e to the power x is asymptotic to x plus 1, since e to the power minus 1 is asymptotic to x?
Yeah, you could say that. Because then you are, x to the power 1 is just a function that like goes like this, and at this point here, is exactly 1, but that's why they do -1, so it approaches the same as 0. But if you say x plus 1 is the same thing as, because if you approach it, it will eventually be exactly the same number. But we'll not go into that too much.
Alright, so these were the questions, I think.
Okay.
Yeah, another question was, what if it goes to minus infinity, but I don't think they have to know that.
No, but if you are curious, what happens if limit from n going to minus infinity, what you just have to realize is that this will all be 0, so this is not a problem then, because if you fill in minus infinity here, actually they will be like -0, but 0 is not positive or negative, so you can't really say anything about that. So to minus infinity, not that big of a problem. But I'm not saying that it could not give you problems. For example, if you have the square root over this, and then you would take fill in like negative infinity, it might give you some problems. But yeah, we're not going too deep into that.
Okay, then one more question, which is basically they ask you to do an example, so I'll show you what they ask.
That one?
Oh yeah, you can see there. Okay.
Yeah. Okay, let's take a look. So we have fx is 3x squared plus 8x divided by 9x squared plus 8x to the power 3, and then divided by 5x power 6, like this. Do you mean this one? Because I see fx and gx, so I'm assuming that you want them to be divided by each other, which of course with the limit of x going to 0. And if this is what you mean, then continue with it, and if not, then I'm not sure what you then mean. Yes, okay.
Yes, that's what she means, yeah.
So first, what we're going to do is write the upper fraction like to the left of it, because this is like a multiplication. So this is actually the same as 1 divided by 5x to the power 6 times 3x squared plus 8x divided by 9x squared plus x to the power 3. And then you would, multiply this top and bottom, but I can already say that the power in the denominator is way bigger than the powers in the numerator. So if you would do that, then you would always end up with problems with dividing by 0. So this limit does not exist in this case. I mean, it could exist if you maybe look at L'Hopital rule, but that's not really explained in this course, so we're not going too in depth on that. It's just that right now with the tools that you've gotten, this limit is not solvable. I hope that answers your question. And that, I mean, how I saw that was just that the power in the denominator is bigger than the power in the numerator. That's already a power to the 6 here. I hope it answers your question, and if not, just let me know. Okay, then we're talking about the geometric series, the infinite sum. And the only thing you have to know about this, really, is I'll quickly show as to why, if you take the infinite sum of a ground number to the power of n, and the power gets bigger and bigger, why that is equal to 1 divided by 1 minus r, if your r is between 0 and 1, because he could ask for this in the exam. So I'm just quickly going to show you how he gets to that conclusion, and after that we're done with the sequences already. So what we're having right now is the sum to infinity and starting with 0 of r to the power of n. And we know that r is in between 0 and 1. And if we have an infinite sum, what we would usually do is if we have an infinite sum, what we would do is actually not look at the infinite sum, but look at a partial sum. So we would decide on an n, so a capital N, to go up until that point. So this would be equal to, of course, r to the power 0 plus r to the power 1, or 2, etc., up until r to the power of big N. And we will define this whole sum as S of n, comma r. Like at what n we start, and the r is like what the ground number is. So we have defined the sum as Sn, comma r, and we want to know what this solution is. So this, let's do that in green, this was of course equal to Sn, comma r. So what we can also define is the sum of n, comma r times r. I mean, if we do it times r, all we do is actually just upping every power that we have up until r to the power n plus 1. So what we can now do is we can say, hey, let's subtract those two things. And you may be wondering why. Well, we can show you, because if we do this, well, the first one was the R0 plus R1 plus R2, etc., minus R1 plus R2 plus etc. until R to the power n plus 1. So what you see actually is that right here we have an r to the power of 1. Let's do actually with the purple. R to the power 1, and also here. Here we have r to the power 2, and also here we have r to the power 2. So those two, because it's in, like, we're subtracting those two, those cancel each other, those two cancel each other out. So what we're left with is r to the power of 0 plus, minus r to the power of capital N plus 1. But we wanted to know the solution to Sn actually, like what this answer is. And right now we have something different here. So first we're going to do is we're going to take out Sn, r like in brackets. We're going to factorize it out. So we were left with 1 minus r times S of n, r. And this is still the same thing what we've written above there, r0 minus rn plus 1. And now we can simply divide by 1 minus r. So we can get Sn, r is r to the power of 0 minus r to the power n plus 1 divided by 1 minus r. And right now we've taken a partial sum. We've just summed up until big N. The 1 minus r is just because I wrote it there. I subtracted the minus the sum here. That's what I did here. I just said I can do the sum normally above here. I could also do the whole sum but multiply it with r. Just why not? And when I write those two things down like this, subtract them, I'm left with just r0 and r minus n plus 1. And indeed, as people said, r to the power of 0, this is 1. And right now we've looked at the partial sum, so we've looked for a specific n. However, if n is close to infinity, or like almost infinity, and your r is smaller than 1 and bigger than 0, the limit of that is actually 0. Because the number will get smaller and smaller and smaller. So we are left with 1 minus 0, so just 1, divided by 1 minus r. And that is why the infinite series, infinite sum, can be equal to this number. And that's the geometric series, and that is why if you have an infinite series like this, that you can replace it with 1 divided by 1 minus r and just fill in r and know exactly what the sum will sum up to.
So there are a few questions, Arjan. Shall I read them for you? Or
I'm not sure like which one you are answering and which.
So the first question is, why does it say minus r to the power n plus 1?
Okay, so right here. Okay, so let's quickly. I'll simplify what I just said, like do it consistently, we have the sum from 0 of n is 0 up until big N. And r to the power of 0, r to the power 1, 2, etc. up until r to the power of big N. Then I have the exact same thing, only this time I multiply everything with r. That's what I have right here. I have s n comma r times r. I multiply with r here. So I have r to the power 1 way up until r to the power of n plus 1 because I multiply this r to the power n, a big N, with r. So that's why I get r to the power of n plus 1. I just multiply this whole sequence here with r. So that's why every power gets 1 higher. And then when you subtract those from each other, because so many terms are repeating, as you can see right here, these two terms, maybe it's not seeable, these two terms are repeating, these two terms are repeating, same as r to the power 3 and r4 and r5 up until r to the power of n. So if those are all repeating and we subtract those two, then we are just left with r to the power 0 minus r to the power n plus 1. Now we are left with Sn minus r times Sn, like this infinite series, but we didn't want that. We want to just know the answer of our series. So if we just take this Sn comma r outside the brackets, so we factorize it out. So this is completely equal to this. We just factorize it out. No, right now big N is just a big number, not infinity. We're just looking at the partial sum, so we're choosing an N, not to infinity, so we can actually like define what the answer will be, and later we can actually extrapolate that or like conclude it for what happens when N it gets bigger and bigger up until infinity. So indeed, that's why we are left with r0 minus r to the power 0 minus r to the power of big N plus 1 divided by 1 minus r, because we just divide left and right by 1 minus r, which was here on the left. And we know that r to the power 0 is 1. And this number is very small, because let's say you have a half and you do that like to the power 2, it's smaller, it's like 0.25. And then you do to the power 3, which gets times a half again. It will get smaller and smaller and smaller. So as n is bigger and bigger and bigger, this number, r to the power of n plus 1, will be smaller and smaller and smaller. But if n, big N is infinity, this number will be so small it is effectively 0. So if this is effectively 0, we actually get 1 minus 0 divided by 1 minus r, which is exactly the same things as 1 divided by 1 minus r. So we know right now we have an infinite sum, and we can actually calculate it if our r is between 0 and 1.
Alright. So someone asked, for s in between brackets n comma r, you can also have r to the power of n, right?
In between the brackets, or?
Yeah, so s and then in between the brackets n comma r.
And what do you want to replace it with?
R to the power of n, big N.
You want to replace s n comma r with r to the power of n?
Yeah. So with big N, r to the power.
Yeah. So s n comma r, you say that is equal to r to the power of big N, like
yeah,
that.
that's what they said. That's what they proposed.
Yeah, that's not true, because we are adding a lot of things together, and if your r is bigger than 1, then you would still add up all these things together, so it will still not be equal. I mean, you could say approximately that. However, if your r is between 0 and 1, then that's not true, because the bigger your n is, the smaller your number will get. So r to the power of big N, or big N plus 1, will just be so close to 0 that is assumably that it's 0.
Okay, then a lot of people ask, do we need to know this proof? I'm not a TA anymore. I was last year, and Luca can do crazy stuff, and maybe he can ask about this on the exam, like prove that
You could also like prove that the geometric series is equal to 1 divided by 1 minus r using telescoping sequences. What it just means with that is exactly what we've done here. We've just subtracted a lot of each other because they are appearing double, like r to the power 1, r to the power 2. So that's what he could ask you.
But
Because
I do
it's
think
crazy.
that the main focus lies with just computing it, right?
Yeah, I hope so. Really.
Yeah, I mean, I don't know if they can hear me, but I think the main focus is with computing.
Yeah, so I'll just repeat that. She thinks that the main focus is on repeating, the understanding and like the computing
Yeah.
part. So filling it in, knowing when you have an infinite series like this and how to calculate it.
Yeah.
Yes, we can hear her too. Okay,
Oh,
great.
Okay, nice.
Good microphone. Okay. Yes, okay. So that was the sequences. Now I'll talk a little bit about functions. After that, we can have like a small break, and then I'll pass it over to Daphne, who can talk about the derivation and integrations. So we have a lot of different functions, and they all have their own properties. We have linear functions in the form of ax plus b, and polynomials where there's also a power added to that. So we have ax to the power n, bx to the power n minus 1, and as many powers as you want, but they are like whole numbers. They're integers. Then you, of course, you have fractions. You can have square roots, logarithms. The thing that was not on here, but is also very important, are the sine, cosine, and tangent functions. Would you talk about that, or did I talk about?
I'm going to talk about those with the derivative and the integral.
Okay, but will you introduce them at that point, or shall I introduce them right now?
You can introduce them
Okay,
right now.
and I'll introduce the trigonomic functions quickly, and then it's off to a break and the derivations. So that was the end of the page, so I'll just open a new one. There we go, clean slate. Good. So the sine, cosine, and tangent, where are they useful for? Well, if you have a circle, which is called the unit circle, I cannot. Okay, this is the hardest part, drawing a nice circle. Okay, I think I did pretty well. What we can actually do is this circle with a radius of 1, we can actually see this as like the x and y, like the plane, and if we have a point on here, we can draw a triangle with 90 degrees. And what is important with this is that if we have such a triangle, we want to know what this angle is, because then we have more information about this point that is on the circle. And when these functions were invented, this was the general idea behind it. When we want to know what this what the angle is of this point. So we have the sine function, and the sine function of our angle alpha is equal to the opposite side. Let's call this M for middle point, P for point on a circle, and this S because why not? Then we have the opposite side, which is PS, divided by the hypotenuse, which is PM. And for the cosine, it is the adjacent side, which is MS, divided by the hypotenuse, which is PM. And this just describes the ratio between these functions. So if you take the sine of the angle, then that is the same ratio as dividing the opposite side by the hypotenuse. No, I'm not removing the charger. I really like to have it in because the performance also stays high at that point. The tangent of the alpha is the opposite side of PS divided by the adjacent side, which is MS. And these are all ratios, so if you want to actually calculate what each angle is, then you can have the, maybe there's a bit of extra information, but if you want just to calculate the angle, you can just take the arc sine or the arc cosine of these two sides and calculate exactly what that angle is. And with this, there's also another form of introducing how to show what these angles are, and normally you would have angles up until 360 degrees for a whole circle, but they're not using degrees, they're using radians. And what a radian is if I can quickly show that, let's do it red, yes, red is good. If we have a half a circle here, yes, so why I'm writing down arcsim because there's a lot of controversy about using this one, because sometimes people assume this is like 1 divided by the sine of x, which it is not. And to avoid confusion, they just write arc sine or arc cosine or arc tangent, which is just the inverse version, but there's no confusion about if it's 1 divided by that or not. I'll just maybe put it there. This is not true, of course. What was I talking about? Oh yeah, the radians. So if we have a triangle here, normally a triangle with all sides, actually let's write that one here. If we have a simple triangle, all sides are exactly the same length, we know that all angles are also the same, all 60 degrees. But what if we want to make one side like a little bit curvy, you know, like that, like on a circle? So if we do that, we can take a rope and of exactly like length 1 and go over this, and we know exactly what this length is. It's also 1. This angle we call 1 radian or 1 rad. And if you do that for a half a circle, we are left with a small piece which has length. This piece has a length of 0.141592, etc., which is of course pi. And this is where pi also came from. It's like half of a circle, and that's why a whole circle is 2 pi. And indeed, if you want to calculate how you can go from the angle degrees to radians, you can easily just use the proportionality, because you know that pi is equal to 180 degrees. So if you want to know, oh, I have 45 degrees, how much pi is that, or how much radian is that, you can just easily multiply these two together, yellow is nice, and divide by 180. So you get pi times 45 divided by 180 times pi, which is equal to 1 pi over 4. So that's how you would calculate between angles and radians. This is like a little bit of background information, because you are going to use trigonometry functions right now just, you know, as a function. However, next year with applied mathematics, you're going more in depth with these functions. So it's real nice to have it repeated for now, and just remembering where this came from and why you use pi in these functions usually. So these are also functions that you can manipulate, which will be shown later with derivations and integrations. And I think that is everything for functions that we have to discuss. Did I miss anything?
Don't think so.
I don't think so either. No, so the thing, even if you want to go from, even if you had to do this on the exam, it's not like that's difficult to go from like degrees to radians, because all you have to do is just keep the pi there. You never calculate with pi. It's just, oh, if you have 30 degrees, you know, 30 divided by 180 is a specific number, you know, it's 1/6. So if you have anything that you would recalculate to radians or something, it would not be that difficult, I would assume. So
yeah, most likely they won't even need it.
No,
I think
true.
The only thing that you might need to know is that, for example, if you have with the derivatives or the integrals mostly, if you have, for example, your final integral is sine and then you have to fill in pi, then you should know what comes out of that. But that's just basic unit circle, and I will cover that in a bit as well. So
yeah, indeed, yeah. Okay, cool.
I think it's time for
No
break.
questions for us? Okay, nice. Then we can do like a small break of like 15 minutes, I think. 10 minutes, I don't know what people prefer. And then after that, it's back to Daphne, who will explain the derivations and integrations, which is the most fun part of calculus.
Hey, that's true.
I love it. Okay.
Alright.
Hope you enjoyed it.
Let's continue at 8 then.
Yes, continue at 8. That's actually what you can have a poor man's overlay. Here. Like this.
Nice.
Nice.
So did you mute the mic?
Um,
I mean, you don't have to.
actually no, but I'm not sure how to. There's like not even a button on it, so I don't know how to mute.
It's fine. They can hear us talk.
I think.
Whatever.
I mean, I could just stop the stream for a bit. I could also do that. I mean, the stream will still be live, I think.
I'm no expert on YouTube, so you do it.
I mean, there's no like
Vegetarian.
reason for not to be.
If it then doesn't continue anymore, I don't know.
Stream part 2.
Yeah, right. Make another one like part 2. I mean, in the worst case, we could do that, but.
Is it back?
Now it's not loading,
Yeah, it's not loading anymore, so.
and I can see your camera.
Oh wait, it's back, right?
Yeah, now it's technical difficulties
Okay.
part 2.
Okay. Thanks for.
Oh,
Like, how is the camera? I don't even. Is the camera like? I don't even know.
Lily has the.
I mean, that's delayed, so we can see actually.
It hasn't started yet. If that's what you.
Right, no, it's
It-
not. We
Now
can
it
see
is.
it up there, though.
Yeah, but like
Yeah.
the live thing is in front of it, so we can see shit.
Oh, right, it's my face. It's my face.
Wait, we are actually streaming the wrong one, right?
We have to.
Yeah, we're streaming.
I don't know. How does this work?
Wait, but not anymore. I mean, yes, okay. I think. Yes, okay, we're streaming
Okay.
the right.
Nice.
Okay, yeah, everything is up.
Okay,
Running.
cool.
The camera is wrong. You just tell us.
So I hope everyone can hear me now. Visible, everything. Yes.
Yay.
All right. Cool. So Arjan just told us about the functions and everything, and the limits and the asymptotics. So we're going to take a look at the derivative and the integral right now. Sorry. For the derivative, I first want to cover the general rule. So the general rule for taking a derivative would be the fx of ax to power n. That will be your general function. And to take the derivative for that, then we could say, I'm kind of distracted. We could say that we take the power of that x. We can take it, take one smaller power and then multiply it with the whole thing. So let me just show an example. Help. Yeah.
Click on
Okay.
the- yeah,
All right.
okay.
Yeah, it's fixed. So I'm getting used to the setup. I'm sorry. So let's do an example just to make it more clear. So that's not good. Hang on. Yeah. Okay. I think it's working out. Oh, I'm not used to this pen. So we have fx. Let's say we have 3x4. If we then want to take derivative from this, we first we can write that either as fx or dfx dx. Either notation is fine because I've got this question a lot, but you can write it either way. It's fine. And we can say we take 4 to the front, so it's 4 times 3x, and then 4 minus 1, so it's 3, and that will be 12x to the third. So this is how you would do a basic derivative, just by taking the power that's currently on the x, take it to the front, and then make it one smaller. Alright, well this is just for a general function for x. Let's say we have polynomials, so they have the form of, for example, ax squared plus bx plus c, for example. This will be a polynomial. Oh, sorry, I'm still getting used to the pen. So if you want to take the derivative of this, so let's see this slide. So we can see that for every part of this derivative, you can just simply look at every part of the derivative and take, or of the polynomial, and take the derivative of that individual part. So let's do an example again, shall we? Alright. Let me go a little bit down. So for example, we can have the function 2x to the power of 4 plus 3x to the power of 3 plus x squared plus 7, for example. Well, if we want to take the derivative of this polynomial, we just look at every part individually. So we can say the derivative of fx is, well, first look at the first part again. The 4 goes to the front, so it's 2 times 4 is 8, x to the third. You can either have f prime or df dx. One of them is enough. I just wanted to state that you can use them both. So this would be the derivative of the first part. Then you can say plus the 3 goes to the front, so it's 9x2. 2 goes to the front, so it's 2x1, but you can leave that 1 out because it's just x. And the derivative of a constant is always 0, so plus 0. And we can rewrite that to, well, everything but the 0. So this will be your derivative for this polynomial then. So yeah, that's the basic principle. I don't think this is too hard yet. Let's go to the slides again. Oh. Okay. So now we do have some more complex functions. So the derivative of ex will just be ex. The derivative of sine will be cosine. The derivative of cosine will be minus sine. The derivative of tangent will be 1 over cosine squared. And the derivative of the ln x will be 1 over x. Please memorize those derivatives, because these are very important, and I think that if you practice a lot with the material, they will get very familiar to you. Alright. So we will do some examples with those in a bit, but for now I will just show this list. We can also sometimes, I've noticed, what was in general quite difficult during the practicals was when we had a fraction in the function, and we wanted to use or take a derivative for that fraction. Well, there's an easy way to do that. So let's say, okay, go down. Let's say we have the fx of let's see, 1 over 2x, and we want to take the derivative of this. Well, there's a general rule that if you have 1 over something, you can also rewrite this to 2x minus 1. That's just a rule. So you can rewrite fractions to the power of x, or the function of x, in brackets minus 1. So if we then want to take the derivative from this, that's not that hard, because you can then, just like normal, you would take the power to the front, so it's minus 1 times whatever is between the brackets, so 2x in this case. Sorry, I was a bit distracted. And then this power will go 1 lower, so it will be minus 2, right? Because we'll just take the derivative of a lower power. Now we also, and I will cover this later again, but we also have a chain rule right here, because the 2x is inside this bracket, so we also do it times 2. So it will, in the end, the answer of this will be minus 2x minus 2. So that brings me right to the product rule. Let me see, so we can go to the slides. Are there any questions, by the way? I don't think so. Guys, no questions,
No.
right? Okay.
Otherwise, we will let you know.
Cool. Alright. So let's get right into the product rule. Again, I'll first show you the general notation, because that is how Luca put it in the lectures, and that is how you will mostly read it. But I'll also give you a simplified version, because I feel like most people prefer that one over the more difficult notation. So let's go down again. So we have the general notation, and that would be df x gx. So basically what this means is you will want to take the derivative of two functions multiplied with each other. That's why it's called the product rule. And how do you solve this? You first take the derivative of df x dx times just the normal form of gx, and then plus the normal form of fx times the derivative of gx dx. So that is how this difficult rule, what this says, but basically you can rewrite this in a more easier way for saying, so we want to take the derivative of two functions of x that are multiplied. We want to take the derivative of that, and we can write that as the derivative of fx times the normal function of gx plus the normal function of fx times the derivative of gx. So these are the notations, but I think it will be most clear if we just do an example together. So let's say we have the function fx, which is sine x times cosine x, and we want to take the derivative of that. So how do we do this? So we've seen here that the first part in this case would be, I mean now it's double fx, but this will be the first function, this will be the second function. So what you do is you first take the derivative of the sine, and if you go back to the slides you can do that later on, I think it will be online still. The derivative of sine is cosine times the normal function of gx, so this normal function just times cosine, then plus, and then the normal function of fx, which is sine, times the derivative of gx, so times the derivative of cosine, which would be minus sine. Well, we can rewrite this, so we can say that is the same as cosine x squared minus sine x squared, because these two are multiplied and this minus comes in front of here, so it's minus. Is that clear? I think it is, otherwise I would have heard from it. Okay, so let's do another example just to get familiar with the product rule. So we can say fx is ex times 2x4, and we want to take the derivative of that, so we can say f prime. Again, this is the first function, this is the second function, so first we take the derivative of ex, we have seen it that is just ex as well, times the normal function of the second part, so just times 2x over 4, plus, and then we take the normal function of this one, so it's just ex again, times the derivative of 2x over 4, which will be 8x3. And then we can simplify this, and this may be a little tricky, but you can basically take out this e from this multiplication. So you can say ex 2x4 plus 8x3. Because these parts are both multiplied with ex, so you can bring it like outside this this brackets, and you can put 2x4 plus 8x3 in there. Do we have to be able to take the derivative of three functions multiplied? I don't think so. I think the product rule with two functions will be enough. Yeah. And could you explain a bit more about ex and log? What do you want me to say about it exactly? Because So yeah, so what exactly do you want? Do you want to know more about their derivative or about their form or the graph? Please let me know. So this is how you would compute the product rule for ex times 2x4.
No, go on.
Oh, sorry.
You're doing great. Sorry.
I was distracted.
I'm not talking about you.
Okay, then it's good. You can do. Alright, so anyway, so this is how we would compute the product rule. So let's maybe like how they relate to each other. Well, alright, so I'll just open. Hang on, I'll get a new clean sheet. Alright. So yeah, sure. So basically you can have a logarithm, and you can most common logarithms are 2 log x, 10 log x, and e log x. These are basically the most common logarithms, and the e log x is the same as ln x. This is just basically another notation because this is like a special case, so it's mostly often written like ln x. And e is the Euler number, which is, I don't know exactly what, like
2.7.
Yeah, 2 point something, 2.7 something, yeah.
2.4.
2 point something. So basically these are special functions, special complex functions that we can use in derivatives and stuff. So a good thing to know is that you cannot have a logarithm of a negative number. So basically the x in the logarithm will always be positive. It's 2.7. I hear 2.7 something. And so for logarithms, and so also for ln, you can only have positive x's. So, and it's also good to know that the logarithm of 1 is 0. So these are some things that are important to know. And what's so special about the Euler number is that, for example, ex, its own derivative is ex. So the derivative is ex, but also its antiderivative is also ex. So Euler is a really special number in that way. So I don't know if that.
Euler is a person, E is a number.
Sorry. I always thought it was called like the Euler number. Yeah, whatever.
Euler's number, yeah.
Euler's number.
He has so many things named after him that after a while they didn't name things after him because he has so many things named after him.
Nice. Yeah. He was a very accomplished mathematician. Alright, anyway, so ex then, or exponential x, has its own derivative and its own antiderivative. So I hope that is enough explanation about these numbers. I think these are the most important things that you have to know in order to compute the derivative. But the exercise 1 we have log. Which log is it then? In the exercises it almost always has been e log. But for the exercise that you didn't really need to know what log it was, but it was e log most of the time, yeah. So, or ln, sorry, l and x. Yeah. Alright. No problem. So we've covered the product rule. I hope that is clear to everyone. And now let me go back to the slide. So we've done this. We've looked at how we would do the product rule, and we've looked at these two examples. And we log x is 10 log x, right? Yeah, it could be, but it depends on like.
Log x? No, is that difference capital letter or not? Because otherwise, not making any sense.
It's just in the practicals we mostly used e log x, but again, it wasn't really of importance. It was just, yeah. Okay, so let me continue on to the chain rule. So the chain rule, again, we have a general notation and a simplified notation. I will cover both and then do some examples again. So the general notation for the chain rule would be if we have the derivative of a function with a function inside it, as it were. divided by dx. Then you first take the derivative of the total function with respect to gx, and then times the derivative of the thing that is inside the function, basically, with respect to dx. So this is the formal notation, but the simplified notation would be gx squared, or prime, sorry, is f prime gx times the derivative of gx. So let me show you an example immediately, because then it will hopefully make more sense. So let's say we have the function fx is cosine 2x7 plus x3. Alright, to take the derivative of this function, we first take the derivative of this total function, so that will be the derivative of cosine, and we've known that this is minus sine, and we just copy what is inside the brackets. But then everything that's inside the brackets also has this derivative, because this is also a function of x. So we multiply this with the derivative of this polynomial that's inside the brackets, and that will be 14x to the 6th plus 3x2. Alright, so this will be the derivative of this then. And if you want, you can bring it to the front, so you can say minus 14x6 plus 3x2 sine 2x7 plus x3. But it's fine. Okay. So a function inside a function, basically, if you have if you have a function with respect to x inside a function with respect to x. So basically, if there's an x in that function still, then it would be then it's not a constant. So whenever it's not a constant, then you should take the derivative of that one as well. So let me do another example. So let's say we have fx is 2 4x squared. Well, first I want to show you the technique that we learned a few slides back, that you can rewrite this fraction with the -1 notation. So you can say this is the same as 2 times 1 over 4x squared is the same as 2 times, oh, that's supposed to be a times, 4x squared minus 1. Okay, this multiplies sign, by the way. And then the derivative of this would be, we take the -1 to the front again, so it will be 2 times -1 times 4x squared, and then the -1 will go 1 down, so it's -2 times whatever is inside here, because this is also a function of x, so we take the derivative of this one as well, so it will be 8x, because this is the derivative of that. Well, and then we can sort of clean up the mess, so it would be minus 16x, because we do 2 times -1 times 8x, so minus 16x times 4x2 minus 2, and this would be minus 16x over 4x2 2, because now that the power has gone one lower, it's not -1 anymore, but it's -2, so that means the 2 is the power of the thing that is in the denominator, and be careful, it's the whole thing that's in the denominator, so also the 4. So you can rewrite this as minus 16x divided by 16x 4, which is minus 1x to the third. So yeah, this is another way of doing the chain rule. I hope that's clear.
Someone disliked the stream.
Why did he dislike it?
Ask them.
If you have any feedback, please let us know.
Most professional way ever.
Only positive likes on this. No.
Only positive vibes. Maybe it's just a misclick and after
Yeah,
you just
yeah,
left the stream,
exactly,
you know, nothing
exactly.
no problem.
Why isn't the derivative of that 2 0? that 2. Because this 2 is a constant, so it, so normally if you have, in polynomials, if you have plus a constant, so for example plus 2, then if you take the derivative of that 2, it would indeed be 0. But now this constant is multiplied with the whole function of fx, so then you would not have to take it to 0 because it's already multiplied with the function, so you don't have to bring that to 0 as well. It's just a constant, it's just there. But if it's in a polynomial and it's on its own, basically, then it will become 0.
And even if you're wondering right now, like why the 2 is still there, when you should, if you are in doubt, just do the product rule on it, and you will see that the answer will be like, just leave the 2 alone. So that will also give you the answer.
Right. Alright, hope that answers your question. Then I have prepared one more example that took both the chain rule and the product rule together. So I think that's a good, because I feel like they would ask that on the test as well. So we can say fx is e2x to the third times sinus phi x. So if we want to take the derivative of this function, we need to use both the product rule and the chain rule. So I would start off with using the chain rule, the product rule, because you know that this is a function of x and this is a function of x. So we first know that we have to take the, so let's call this, let's just say we first take the normal function of this one times the derivative of this one. So the derivative of sine is cosine 5x. But you also have to take the derivative of what's inside there, so that would be the chain rule, so times 5. Plus, and now we take the derivative of this one. So that will be e2x3, because remember, the derivative of e is always just itself. However, whatever is in this power is also a function of x, so we have to take the chain rule for that. So we can say times the derivative of 2x over 3. Well, take the 3 to the front, so it becomes 6x2.
Not for children, this term.
Times just the normal function of the sine again. So times sine, oh, it's not gonna fit, 5x. Oh, shit. Sorry. Where is it? Okay, let's back on. 5x. Alright. We can simplify this again. So we know that we can take the e to x3, we can take it here, and then we can say 5 cosine 5x plus 6x sine 5x. So we can simplify it like that. Oh, 6x squared, by the way. Alright, so this would be the solution to the derivative of this function with both the product rule and the chain rule. I hope that makes sense. If not, please let me know. Alright. Okay. So now we can use these rules to work out optimization, because we use the derivative for optimization. And optimization is basically a problem where you have a function and you want to find at what point there's either a minimum or a maximum. So how do we do this? I wrote down a sort of like a guide in the slides to show you how this would be done. So first, for fx, you take the derivative of f. Do we only have to know? Milu, for the derivatives, only the product and the chain rule, and just the normal way of taking a derivative. So to do optimization, you would first take the derivative of fx. So you have a certain function, you take the derivative of fx. Then you solve for the first derivative, you put it equal to 0, and then you solve for x. Then you get, for x you get some points, and these points will probably, will have your maxima or minima. But we still have to compute whether this point is a maximum or a minimum. So what you then do is you take the second derivative, and once you've computed that one, you will fill in these points, and you will check whether it's positive or negative. And if it's negative, you have a maximum for a certain x, and if it's positive, then you have a minimum for that certain x. So for that value that you put in for the second derivative. Alright, okay. So let's do a example again. Let me here. Go back to the alright. That's full. Let me get a new one. Alright, so let's assume we have a function. So fx is e to x times 3x4. This will be our function. To compute either the maximum or the minimum, we first take the first derivative. So we know now that this is computed with the product rule. So we first take the derivative of e to x, which will be e to x, because each derivative is always the same. And now with the chain rule, times 2, times the normal function of this one, so 3x4, and then plus, and then the normal function of this one, so just 2e to x, times the derivative of this one, so that will be 12x to the third, e, alright, and we can rewrite this by saying e to x, 6x to the fourth, plus 12x to the third. Alright? So now we should say fx is 0 gives, and then we solve for that. So we say 2x, 6x4 plus 12x3 is equal to 0. Immediately I have some notes about this because e to x can never be equal to 0. So you can basically just, well, skip that, I don't want to say, but I'll always write it down like this. So we can say e to x is not equal to 0, or 6x4 plus 12x3 is equal to 0. So we then have to solve this equation. So how could you do this? You could say we take x3 out, so it will become 6x plus 12 is equal to 0. So x to the third is equal to 0, or 6x plus 12 is equal to 0. X is 0, or 6x is minus 12, and then x is minus 2. Alright. So now we know what the values are for our minimum or maximum, but we still don't know whether or not it's a minimum or maximum. So we have to compute the second derivative and then put these values in, so this one and this one, to check for every x if it's a minimum or maximum. So how do we do this? We let's see. So the first derivative was, I'll write it down again just for clarification, e to x, 6x4 plus 12x3. Alright, so now we take the second derivative, which is basically just the derivative of this one again. So we can again use the product rule. E to x times 2, so we first take the derivative of this one again, times the normal function of this one, plus, and then we take the normal function of this one, so e to x, so it's not gonna fit, hang on. Alright, I've learned from my mistakes. And then the derivative of this function, so 24x to the third plus 36x to the second. Alright, it fits. And we can again write down this e outside of it, so it'll be 2x, 6x4 plus 12x3 plus 24x3 plus 36x2. Alright. And then we can simplify this even further. So we can say it's e to x 12 x4 plus 24 x3 plus 24 x3 36 x2, which is e to x 12 x4 plus 48 x3 plus 36 x2. Alright, so this will be the second derivative. And so we saw that for x is 0 and x is minus 2, we have a minima and a maxima. And now we want to fill those points in for the second derivative. So we can say, let's see, we can say f minus 2 would be e2 times 2 minus 2 times 12 times minus 2 to the power 4 plus 84 times minus 2 to the power 3 plus 36 to the power of minus, or 2 times minus 2 to the power of 2. Alright. So we can simplify this again. So we can say e to the power times minus 4 times 12 times, this will become a positive number because it's to the power of 4, so it will become, I think, 64, but I'm not 100% sure right now. Or no, 16, of course. Oof, how do I? Hello. Yeah, so plus 84 times, and this one becomes negative because it's to the power of 3, so times minus 8 plus 36 times 4. And now I'm too lazy to compute this all because we can already see that this whole thing becomes negative, right? Due to this minus. And this is just 1 over e to the power 4. So we can say for the second derivative of minus 2, we have a negative number, and thus we have a maximum. Alright. Then for f for 0, we have e2 times 0 times 12 times 0 to the power of 4 plus 84 times 0 to the power of 3 plus 36 times 0 to the power of 2. And so this would result in 1 times 0, which is 0. And now this would mean that you don't know whether it's a minimum or maximum, but this is a saddle point, and to actually solve the saddle point, and to actually solve this, you would have to take the third derivative to figure out what the minimum or the maximum would be. But that's just some background information. You probably don't have to know this for the exam. So most likely there will become it will be a negative or a positive number, and then you'll know whether it's a minimum or maximum. So I hope that is clear. Yeah. Okay, let me go back to the slides. Then sometimes when we have, so for the first derivative, can you show how to prove the derivative using definition of the derivative? That's a very good question. I actually don't have the definition at hand right now, so I can answer that question later on Discord. Right now, I'm sorry.
You also do that at the end of the thing. I know how to do it. So
okay, that's nice. Then Arjan will show you at the end of the workbook. How late is it, by the way? Because I don't know if I'm.
It's 36. So you have like maybe 9 more minutes to finish up the optimization with the steepest descent rule. Then you can have like a small break and then do the integration.
Yeah. Okay, that's cool. So we finish optimization and then we will take a break. All right. So optimization is or the steepest descent rule is basically used when you have a very difficult or first derivative and you cannot solve it for putting it equal to 0. So what we can do then is we can also use the steepest descent rule. And basically how that works. So let's assume you have a graph that looks somewhat like, oh, that's a very ugly graph, hang on. Something like this. And you know that the minimum is right here, but you cannot compute it for some reason. So what you can do then is you can take a random point, a random starting point, and you can make small steps, so like updates, to find that minimum. So we actually have a rule for that, and that is the update rule, which basically states that for every Ariel.
It's a good question for people as well.
I mean, it was covered in the practical, but I told you it was used when if you have like a derivative for, so like if the first derivative has, for example, a power of 3, and you put it for x to the power of 3, and you put it equal to 0, and you cannot solve it, then you can use this method instead. So if you cannot manually solve this, then you could use this step rule. Spoiler for future code. Okay. Didn't they already have it with Intro to AI as well? Maybe?
I don't know.
Did they?
I think we did it last year, but I'm not quite sure. Anyway, Bulgarians will probably be not. No, I mean I'm covering it right now because we did it in the practical, but it's basically if they ask something about it, it's most likely that you have to compute the derivative and then put it in the update rule. But I'll come to that in a bit. So basically what this rule means is that for every next x that you will be looking at, you look at the x that you're currently in, so that's xn minus, and then eta is the update, like the learning rate or the step rate, and basically eta defines with what how big your step is that you're going to take, and then times the derivative, because the derivative shows you at what angle you're going to take that step, so it basically shows you the curve of the graph. So this is the update rule. So what you can do is you can take the derivative of a specific function that you're given. So let me see if I have an example on this actually. No. Okay, well, if you have, so for example, if you have the function, a very hard function, I can't think of one on the top of my head, but basically you take the derivative of that one and you can literally just put it in this update rule, and that would give you the steepest descent rule. So that is how you would compute it. So let's see. Yeah, so we can also do optimization with Python. Code, nice. So we didn't have code. We had code for this, but it's not on the slide. Hang on. Okay. Yes, let me show it to you. Arjan, where can I type the code?
Go to Notepad++. It's like on the bottom left corner.
Hang on, what's happening? Panics.
Just escape.
Oh, okay.
And then just go, okay.
Alright, thank you. So let's say we have wait, first let me go to, let's say make a new thing. Alright. Assume we have the function fx is x3 minus x2 plus 4, and we know that the derivative of this function is 3x squared minus 2x, and for fx is 0, we get x is 0 or x is 2 over 3. And then we know that the second derivative is 6x squared minus 2. So we can also plot this graph in Python just to check whether we see what maximum we get. And so how you would do this now? Yeah, so I go back to the code. So we can define, first we can define our f. So we can say, alright, f, and then we use the lambda notation like you're used to in the work group. So we can say is lambda x. That basically means that you're going to define a function f which uses x, and lambda is just a lambda expression. You will learn about those later. X squared minus. So x and then double stars means to the power of, and 1 star means times. So this was our plus 4. So this is how we define f. And then we can plot the range in the range that we want to plot it. So we can say, alright, we use, this is just the notation that you use with it. Lim space 0.5. Sorry. So this would be hang on, I'm confused myself now. Yeah, so you plot it from minus 0.5 to 0.2 with very small. So like with could you type this a little lower? Of course I can. Can you see it now? And with steps of 100 basically. So that will be the range, and then we can say, all right, we found your face. Yeah, we can really see. Yeah, I think it fixed now, but it's just a delay. All right. And we said that we found for x is 0 and x is 2/3, we found a maximum and a minimum. So we can compute it like this. So we can say x1 is 0 and x2 is 2/3. And then we can use the plot function. So we can say plt.plot for the x range, so for the range that we defined, and then f x range. So this is how you will plot it, and then to make two nice lines in those plots to show for which x we have a minimum or maximum, we can write it like this. So we say x is x1, so x1 is the 0, it's what we defined on top of that. And C. Oh. And okay. Oh, label. Typing on another man's laptop is hard. It's
My laptop is cool.
Your laptop is very cool, it's just I'm not used to it.
Thank you. It's almost getting mad.
Luckily you didn't. So basically what this lines means is that we use the x1 and the ls is just showing you to get dotted lines, and the label is basically a legend that will be in the top of the graph, and it will basically say, okay, so the dotted line is x1. So this is just some code to make your graph nicer, so we can do that for x2 as well. And this is the color, so C is red, CK, not quite sure what color it is, but it's color. Right. And then we can say plot the legend local is best, so that basically means the location is wherever it's best shown. So this is how we plot the optimization problem, and I can show you. We don't need to know this for example. Yeah, you should be able to recall a little bit of Python in the exam. That's why I just give you this example, because so I'm not sure whether he's going to ask you to plot the optimization or the derivative or an integral, but if you look at the practice exams as well, you can see that you have to know some Python, but it's most likely just going to be one exercise. So yeah, some Python will be in there. So what the graph will then look like. He said there won't be plots. Oh, I didn't know this, because he doesn't really tell us a lot. Alright, then there won't be plots. That's nice. Then, never mind the plot. Then we can. So this is basically how you will plot this. This means just plotting it for x1, for x2, the color, type of line, and the label. But if you don't need to know this, then that's fine. Then we can skip it. Then I think we arrived at the integrals. Oh, yeah. Yeah, so we arrived at the integrals, so I think we'll be taking a little break now, guys.
Yeah, it's fine. Yeah, are you done with the
Yeah.
steepest descent? Okay, cool.
Yeah.
We're going to take a small break of 15 minutes and be back at 9.
Okay, we will be back at 9 I hear. So, alright. See you at 9. How do I stop this?
Okay, I'll stop it for you.
Yes.
Is if you have a function ax to the power of n, then the antiderivative will be a times 1 over n plus 1 x n plus 1. Again, this may be a little abstract, so let's do a example. Yep. So let's say we have the function for x2, and we want to take the antiderivative. So that's denoted with the big F. So how do we do this? Basically, what you do is you up the power with 1, so it's 4x and then 2 plus 1. However, if you take the derivative of this thing, it would be, again, it should be the same as fx. However, if you take the derivative of this, 3 will go to the front and will be 3 times 4, 2. However, that's not the same as this one, so we have to cancel that 3 out, and we basically do that by using 1 over 3 times the whole thing. So the antiderivative for 4x2 will become 4, 3x3. I hope that step is clear. So that's a basic concept of the antiderivative. And we also have antiderivatives for more complex functions. So again, I will show you the list. So we have ex, well, the antiderivative, just like the derivative of ex, is ex again. The antiderivative for sine is minus cosine. The antiderivative for cosine is sine. And the antiderivative for 1 over x is ln x. These are just, again, functions that you should know, and you will get familiar with them if you do the exercises. So these are important to memorize. And let's do some examples to again get a feel for how it works. So let's say we have fx is, now I have to look back at what it was. Yeah. So let's say fx is e to x. Then fx would be e to x again, because the antiderivative of e to x is just e to x. However, if you take the derivative of this one again, due to the chain rule, this 2 will come out. So to cancel for that, we do 1 over 2 e to x. So that will be the antiderivative then. What the hell's going on?
We're just showing each other memes.
Nice. Okay, so let's do yet another example, because this might be a little weird at first, but practice again and it will become clear. So let's say we have cosine 5x, and we want to take the antiderivative of this. Now we first take the antiderivative of cosine 5x. Well, that will be, the antiderivative of cosine is sine, so sine 5x. However, with the chain rule, this 5 would come out. If you take the derivative again, we don't want that to happen, so we do 1 over 5 times sine 5x. So that is the antiderivative of cosine 5x. So that is how that works. And let me go back to the slides again. Alright. So that is how to take antiderivatives, and these are important for integrals later on. So let's get straight into it, and let's talk about the fundamental theorem of calculus, as Luca always calls it. And that basically denotes that if you have an integral from the interval a to b, then that will be it will be noted as the derivative of the antiderivative dx is, then we take the antiderivative of this whole integral, which is the antiderivative of b minus the antiderivative, or sorry, the antiderivative of this function here, and then put b in minus the antiderivative of that function with put a in. So a notation I personally always learned at high school was if you have the antiderivative or the integral for a to b of fx dx, and dx just means that you take the integral with respect to x, then you can take the antiderivative of fx, and then for the integral of a b, this is basically the same notation as these square brackets. and that would be the same as fb minus fa. So let's do an example to make this more clear. So let's say we have the integral for alright. So let's say we have the integral for 0 to 2. Hello? For 0 to 2. For 2e to x plus 3x5 dx. Then what we do is we first take the antiderivative of this function. So we can write that down like this. So the antiderivative of 2ex would be 2e to x, because the antiderivative of e is always itself, times 1 over 2, because this 2 will come out, we don't want that to happen, so we do it 1 over 2. Plus, and then the antiderivative for 3x5 would be 1 over 6 times 3x6 for 0 to 2. Alright, let's simplify this a bit. So we get e to x, because this 2 and this 1 over 2 cancel each other out, plus 1 over 6 times 3 is 1 over 2, x to the power 6 from 0 to 2. Alright. And now we can fill in this 0 and this 2. So that's basically the step that, so if we write this in another color, so that would basically be the step for fb minus fa. So how do we do this? We can write it down as follows. We can fill in the 2, so we get e2 times 2 plus 1 over 2 times 2 to the power 6 minus, and now brackets are very important because sometimes this minus will make something that's negative in here positive again, so beware of the brackets. E2 times 0 plus 1 over 2 times 0 to the power 6. So that will be e to the power 4 plus 1 over 2 times 46 minus e to the power of 0 plus 0. And that will be e to the power 4 plus 32 minus 1, because something to the power of 0 is always 1, so that will be e to the power 4 plus 31. So that will be the solution of this integral. Alright, let's get to another example as well. Take a new sheet. Alright. So let's also do one with a complex function. So let's say we take the integral for 1 over 2 pi cosine x dx. Alright, well, then first we need to take the antiderivative of cosine x, and can you do an example of integration by substitution? Yeah, we'll get to that in a bit. So we first do normal integration, then integration by substitution, and integration by parts. So we'll get there. So we first take the antiderivative of cosine, which would be sine. So we can put those in the square brackets again. Alright. And then from the interval of minus a half p. So we can solve that. We can say sinus and then put in a half pi minus sine minus a half pi. And as Arjan just explained the unit circle, let me draw it. It's not the best circle, but it's something. So this would be a half pi, this would be 0, this would be pi, and this would be 1.5 pi. And let's take another color. So this axis would say something about the sine, this axis would say something about the cosine. Alright, so now that we fill in a half pi, we can see that this one is up here, and we know that this would be the 1 for sine, because it's a unit circle with length 1 everywhere, so this will be 1, this will be minus 1, so 0, comma, minus 1, 0, comma, minus 1, and this will be minus 1, comma, 0, and this will be 1, comma, 0. And so in this case sine would be 1, so this is how we would then solve without a calculator, because unfortunately you cannot use those on the test. So we can say that sine of a half pi is 1 minus, and then sine of a minus a half pi, so that will be over here, and that will be minus 1. And now we can say that this minus 1 is 2. So that is why these brackets are very important, because these minus cancel each other out, so it becomes plus. So please be aware of the brackets and use them carefully. So this will be another example of a simple integration, so this answer will be 2 then. But indeed, as was mentioned in the chat as well, we also have a more difficult integrals. Yeah, so this is the unit circle, but then in its full glory. So this is basically what I drew, but a little bit more complicated. Yeah, so let's take a look at integration by parts now, because that is another very important phenomenon. And basically what it means is that if you have an integral with two functions that have x and they're multiplied with each other, then you solve them in a different way. And I will show you both notations. So first the complex notation, then I will simplify it again and I will do some examples. Let's see. Alright. So let's get back to code. Alright. So first, integration by parts. We have the general notation, which basically is from an integral from a to b. We have dfx dx gx is f b g b minus f a g a. Ooh. I'm going to move this around a little. Okay. Minus the integral of a b fx, then derivative of gx. Yeah. So this is one way of notating it, but how I would prefer it is a b fx gx. So basically you have an integral. You have an integral with one function that is basically already a derivative and one that is just a normal function, and we can then rewrite this to fx gx for the interval ab. No, you shouldn't. You don't have to draw that. You can just immediately write sine a half pi is 1. You don't have to draw the circle. It's nice if you don't know it by heart and you can draw it, see what it is, but you don't have to draw a circle. So this would be another notation. This is the one I'm going to use, and I can best explain this by just giving you an example immediately, so we can do this together. So let me see. So let's assume we have the integral for 0 to 1, 2x e 2x dx, and so we have to determine which of these is fx and which of these is gx. Well, in this case it's like this, because we can easily take the antiderivative of e to x, and we can easily take the derivative of 2x, because later on, as the formula states, we will have to convert the derivative of x back of fx. We'll have to convert it back to a normal fx. So to do that, we use the antiderivative, and then we have to convert gx to the derivative of gx, as you can see here. So we have to take the derivative of that. And it's nice to take 2x as gx because if we take the derivative of 2x, this will result in a constant, and then we can simply solve it for like how we're used to solve an integral. So I always write down like a mental note, like okay, we take fx is ex and gx is 2x, and then we want to rewrite the derivative of fx, so that will be just fx, and to do that we use the antiderivative. Oh, this is a 2 by the way. So the antiderivative of e2x is 1 to 2x, we've seen that one before. And then we want to take g to the derivative of gx, so that will just be 2. Alright. So now that we know this, we can rewrite the integral according to the rule above. So we can say this is equal to, and then we take normal function of fx, which was 1 over 2 e to x, times the normal function of gx, which is 2x, 2, 1, minus the integral for 1 to 0, and then we take normal function of f, so we compute that, that will be 1/2 2x, times the derivative of gx, so that will be 2. Alright, and now we can solve this because we can just say, so that is this one, 2x from 0 to 1 minus, and now to solve this integral we can rewrite it by the way as e2x, because the 2 and the half cancel each other out. So now we take the antiderivative of e2x, and that would again be 1/2 e to x for 0 to 1. So we basically solve this integral, and now we can just fill in the numbers. So we can say, alright, we can have 1 over 2 e times 2 times 1 times 2 times 1, so we fill in the 1, minus, again brackets are important, 1 over 2 e times 0 times 2 times 1, minus, I'm going to do it to the right, okay, minus, and then we fill in the 1 for this one, so e to 1, minus 1 over 2 e 2 times 0, alright, and now we solve this, so we can say this is 1 over 2 e2 times 2 minus this all, how do you know if you should do integral part twice? I will give you an example in a bit, yes. So this whole part will become minus because you do 2 times minus times this part, so it will just become minus. Minus 1 over 2 e2 minus 1 over 2 e0. Alright. So that will become e over 2 minus 1 over 2 e over 2 plus 1 over 2 e0, which will be, let's see, 1.5 e2 plus 1.5 times 1, so 1.5 e2 plus 1.5. So yes, we know that we don't have to do the integration of parts again, because this only contains one function with x in it. So if you would have a resulting integral with still 2 functions of fx in it, then we would have to take the integration by parts again, and I can give you an example for that in a bit. But for now, it's only one function, so the chain rule is that way of 1 over 18. Sorry, is the antiderivative or 1 over 2? Yes, Robin, that would be the antiderivative, but we right now we take the antiderivative of this whole part, and since this 2 and this 1 over 2 cancel each other out, we just choose e to x. So we take the antiderivative of e to x, and that will be 1/2 e to x. Alright. So this is one of the examples. So let me do another example of integration by parts, but now with double integration. So yeah, okay, let's open a new. Alright. So assume we have the integral for minus a half pi cosine x squared dx, and then we can say that we can take the derivative of fx to be cosine x, because we can easily take the antiderivative of this, and gx we define as x squared. So now we can bring this to fx by taking the antiderivative, and the antiderivative of cosine is sine, and take the derivative of gx, so that will be 2x. Alright, hang on a bit. Okay. Hang on, I'm trying to get back to my notes. Alright, so we can then rewrite this integral as follows. So we can again say we take the normal function of f, so that will be sine x times, and then the normal function of gx, so x squared, for minus 1/2 pi, minus the integral for 1/2 pi. And again, we take the normal function of x, so sine x times the derivative of g times 2x. Now, as you can see, so this is basically Jesse's question. This part still has two functions with x in it, so we have to take the integration by parts again for this integral. So I'll do that in green first. I'll first only solve this integration, and we'll come back to this one in a bit. So again, we want to solve the integration for minus 1/2 pi, and then for sine x 2x dx. Oh, sorry, this needs to have a dx as well. So we can again make like this mental note, so we can choose f derivative x to be sine x, and then fx with use of the antiderivative will become minus cosine x, and then gx will be 2x, and then the derivative of gx will be 2. And now this is good because now we only have a constant left, so we can say that is the same as the normal function of fx, so it will be minus cosine x times the normal function of gx, which will be 2x, for minus 1/2 pi minus 1/2 pi, and then for the function of fx, so minus cosine x times 2. So that's the derivative of gx. So okay, we can substitute this part into here. So we have basically solved this integral. So we can now say, I have to write very small. So we have the 1/2 pi minus 1/2 pi cosine x squared dx. So this was the initial integral that we wanted to solve. We know this part will be there anyway, so we get, sorry, I have to sine x squared for 1/2 pi minus 1/2 pi, and now minus this integral, and we've seen that that is the same as this. So we do a very big bracket, because brackets are important, and we can say minus cosine x 2x for minus 1/2 pi minus the integral for minus a half pi for minus cosine x to dx. And close the bracket. Alright, so now we can solve this big mess. So we can again say sine x, x squared a half pi minus a half pi minus, and then this big bracket again, minus cosine 2x, oh sorry, not 2x, x 2x a half pi minus a half pi minus, and now we take the antiderivative of minus cosine times 2, and the antiderivative of cosine is sine, so the antiderivative of minus cosine would be minus sine, because you just put the minus in front, and the 2 is a constant, so the constant will stay there, so it's minus sine x for a half pi minus a half pi. Alright, and now we can fill this in and we can solve this integral. So we can say, alright, that is sine a half pi times 1/2 pi squared minus sine minus a half pi times minus a half pi squared minus, oh, this is not gonna fit on one page, minus, now we solve this one, so we can say minus cosine 1/2 pi times 2 times a half pi minus, again big bracket, minus cosine minus a half pi, oh this is not going to fit, minus cosine times 2 minus a half pi, sorry for the small part, and then minus, and then we've solved the last one, so it's minus 2 sine 1/2 pi minus 2 sine minus 1/2 pi. So as you can see, these are a lot of brackets, a lot of minuses, so that's why it's really important that you should carefully work this one out. And let me see. Okay, so we can say that this is, so sine is a half pi. If we use the unit circle again, we could find that that is 1 times a half pi squared minus, and then sine minus a half pi is minus 1 times a half pi squared minus minus cosine a half pi is 0, so times 2 times 1/2 pi will just become 0, minus, there's a lot of minuses. So the minus cosine of minus 1/2 pi is, hang on, now I'm making a mess myself. Give me a second, hang on. Hang on, I made a mistake somewhere. Nice. And this is why you use minuses and brackets. Let me see, so minus cosine. Okay, I'm sorry, I don't want to dwell too long on this to find my mistake, but basically this is just another example of why you should really use those brackets and work them out carefully. But basically, if you would work this out in a proper way, you would get 1/4 pi squared plus 1/4 pi squared minus 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 2 minus 2, which would result in 1.5 pi squared minus 4. So it will be 1.5 pi squared minus 8. So this is, so sorry for the rough working it out, but I think that part is quite easy, just filling in the numbers here and do it very carefully. But so the really important part about this is, so we have the double integration by parts, because if you integrate by parts once and there's still two functions left with x both in them, then you still have to integrate one more time until there's only one function with x and a constant. So I hope that is clear. Alright, then I want to, I don't know how I'm on time, by the way.
You are, so have like 13 minutes before like 9:45.
Okay.
Because it's like just past half
Okay.
10.
Then I'll go to integration by substitution, because that is very important as well. Alright, let me open a new. Oh. Alright. So let's go to integration by substitution. Parts. Yeah, so with integration by substitution, we basically use this if we have a integral with a very difficult function on x that we don't know the antiderivative of. So if that is the case, then we can take the integral by using integration by substitution. And I would like to show this to you by using an example. So let's assume we have the integral of x e x squared dx. Now, you know the antiderivative of ex is just ex, but for x squared, the antiderivative is really hard, and we cannot, like, I don't know how to compute that by hand, so then we can use integration by substitution to substitute this x squared to make it more easy for us. So we can, so I will give an example. So we had from 0 to 1 we had x e x squared dx. So taking the integral for x squared is really hard, so we can, let's say yx is x squared. Well, that is nice, because now we can rewrite this integral as ex yx dx. Well, that's nice and all, but now we cannot take the integral, because then we should have had the yx, because we want to take the integral with respect to yx now, because that is our new function that we integrate on. So a trick to rewrite this so that we can take the integral with respect to dyx is by taking the derivative of dyx. And now I'm going to use the formal notation, because then you'll see in a bit why we do this. So we can say that dyx dx, that's basically is the same as saying yx derivative is 2x. And we do this because now we can say, alright, so if that's the case, then dx is dyx divided by 2x. So we can basically rewrite this fraction. Then this we can rewrite even further, so we can say dx is 1 over 2x dyx. Okay, that's good to know, because now we can, so let me get another color. So for dx, we can put this in here. So how would we do that? So we then have the integral of 0 for 1 x e yx dx, and that would become 0, 1 x y x times 1 over 2x dyx. So basically substitute this dx for this part. And we can rewrite this, so we can say for 0 over 1, and then we can bring this 1 over 2x, we can bring that to the front, so we can say that will be x over 2x times eyx dyx. And then we can say that is the same as the integral for 0 to 1. 1 over 2 e yx dyx. Well, that is nice, because now we just have to take the integral like we're used to, but now with respect to yx. So we can actually do that. So we just take the antiderivative of e yx again, and that would be just 1 half e yx, because the antiderivative of yx or e is itself, and then there will be nothing that comes out of this, so it's just e yx as comes out. But what if that is not possible? Most of the time, the exercise that you'll get, then it is possible, because otherwise, yeah, it won't work, of course, because then you have x and you cannot solve that with integral. So yeah, that's a good question, but basically most of the time they will cancel out. So from 0 to 1, yeah, so then we can say that is the same as e, and then we substitute yx back, so yx was x squared, so we can say from 0 to 1, and then we can fill it in like we're used to, so we can say a half e1 squared minus 1 half e0 squared, which is 1 half e1 minus 1 half e0, which is 1 half e minus 1 half, and if you want to rewrite that, that will be 1 half e minus 1. So that is how you take the integral by substitution. Let's see what I have in the slide. So yeah, that's basically the steps that I just took. So take the integral with respect to how. Okay, let's do another example to make it more clear. All right. So let's see. I've had an example prepared. Hang on. Okay, let's do an example for 0 to pi sine x e cosine x. I think this was also one that we had in the practical, but it's a good practice one. So, okay, so we don't know how to take the antiderivative of e to the power cosine x, so we can substitute that cosine for yx. So we can say, all right, yx is cosine x. Then, according to our steps, we take the derivative of yx again. So that will become minus sine, because the derivative of cosine is minus sine. And then we can say, alright, cool, so dx is then dyx minus sine x. So that's basically just rewriting this equation. And then we can rewrite this even further, so we can say dx is 1 over minus sine x dyx. Alright, and so that is nice, because now we can use that again, so we can rewrite the integral then, saying 0 pi sine x e yx dx will become 0 pi sine x e yx, then times 1 over minus sine x dyx. So we again substitute this part for this part, and then we can, oh, my thing is almost full, then we can say, alright, this is the same as 0 to pi, bring this part to the front, so it will be sine x divided by minus sine x e yx dyx, which we can see that cancels out, so it will become minus 1 times e yx dyx. And now we can take the integral again like we're used to, so we can say, alright, the antiderivative for minus e yx is just minus e yx for 0 to pi. And let's see, we can then substitute yx back, so we can say that that will be minus y cosine x b to 0, and then we can solve this So we can say minus e cosine pi minus e cosine 0. And now my sheet is full. Oh. Yeah, so don't really want to get a new one. Alright. Okay, I'm going to refresh it then. So I will recap what we had as last. So we did minus e cosine x for 0 to pi is minus e cosine pi minus e cosine 0. Now with the unit circle we can then say, okay, so cosine pi will be minus 1, so we get minus e minus 1 minus, and then brackets again, minus e, and then the cosine of 0 is 1, so like this. We can rewrite this, so minus e minus 1 minus minus will become plus e1, and we can rewrite this by saying, okay, that's the same as minus 1 over e plus e, so that will be e minus e over 1. So that would be another way to use the integration by parts. I hope. Or the integration by substitution, sorry. I see no questions in the chat, so... Oh, it's going a bit fast. Oh. So, Yuri, at what point did you lose track? Please let me know and I can do that part again. And also you can watch this back, play it over as many times as you like, of course, but please let me know what it's unclear for you. Last page, halfway something. Okay. So, to be honest, I don't know exactly where I was last page halfway, but so basically what I did, we have the integral, we substitute yx for any x that is, or any part that is hard to solve with the integration. So in this case that will be yx is x squared. Then you take the derivative of the yx and you can then change dx to a form of a function times dyx, and then you can fill that in for your integral, and you will then you can then simplify the integral and then solve the integral with respect to yx. So that these are the basic steps that you have to take. If you follow these steps, then I think you'll manage to figure it out, and also you can rewatch this stream later, pause it where you don't get it, and then continue. I'm sorry if I went a bit too fast. So I hope it's fine that way. Also because we don't have that much time left anymore, so... Alright. Yeah, so the last thing that left us to do is to look at integration in Python. Oh, if there's time left, could you also show how to integrate what substitution directions? I mean, I can do that one as an example right now. Wrong button. I can do that one right now, and I'll try to go a little bit less fast. So that will be, I think I have it still in this notebook somewhere. Alright, so that will be the integration of 0 to 1 x3 ex4 dx. Alright, for yx we can now substitute x4 because we don't know how to take the antiderivative of e to the power x4. So that will be your first step, determining what you want to substitute, of course. Then you take the derivative of the yx dx, which would be 4x to the 3. and then we can say we can figure out what dx is by looking at this equation. So we can say dx is dyx divided by 4x3. So we basically shift this equation around, and we can rewrite this by saying 1 over 4x3 times dyx. So basically we bring this one out of the fraction. Alright, so then we can substitute those things into the integral. So we had the integral for 0 to 1 x3 e x4, and then dx, and we can rewrite this now to x3 e yx times, and we change this dx to this part, so over 4x3 times dyx. Alright, we can then bring this part to the front, so it will be 1 over 0 1 4x3, this is a 3, times x3 times eyx dyx, which can be rewritten to 0 over 1, then we say x3 4x3 times eyx dyx, and we can simplify it even further by saying 1 over 0 1 over 4 eyx dyx, because these x's cancel out. Alright, then we take the antiderivative of this thing again, so that will be 1 over 4 eyx, because the antiderivative of e is itself. There will not be anything if you take derivative of yx again, there will not come anything out of it, so it's just 1 over 4 ex from 0 to 1, and that will be let's see, then we will just fill in, or sorry, no. Then we can rewrite this again, so we can substitute the y back, so we can say yx was x4, so we can put it here for 0 to 1, and then we can fill it in, so it's 1 over 4 times e1 to the power 4 minus 1 over 4 times e to the power of 0 4, which will be then 1 over 4 e1 minus 1 over 4 e0, which is 1 over 4 e minus 1 over 4 times 1, because sum to the power 0 is always 1, which will be 1 over 4 e minus 1 over 4, and you could even write this as 1 over 4 e minus 1. So that is how we would do that one. I hope that is clear. Sophie, I think, asked. Yeah. If you have time, could you please indicate both sign x, e, x? I'll first continue with the Python code, then let Arjan explain something else, and then if we have time left, we can. Otherwise, if that is one of the questions from the practical, the answers of the practical are also online now, so you can check those as well, Maddie. So let's continue to the Python code real quick, because you need to write some Python code as well. Again, it's not in the slide, so I'll just type it myself. Okay. So I think this is then more important, because some of you told me that you won't have plots for Python, but you will have computations then, I assume. So a way of defining a integral, or like approximating an integral in Python, is by, well, first of all, you always have I've got it for the last Python code, but you also have the import numpy s and p. That's just a basic library that we import so that we can use it to compute certain functions. So n is 20. I'm just going to type some things and then explain them in a bit. So first we define our interval, which is a is 0 and b is 1. So that will basically just be the integral from 0 to 1. And n will be the approximation of, well, let me show you this in a drawing actually. So, that's fine. So with Python, basically what it does, so let's assume you have this curve, for example, and this is your... Alright. So basically what the integral does is it approximates the area under the curve. So it basically approximates this area, right? So let me use another color. So to do that in a Python code, basically what the code does is it will make boxes. So it will make a box here, and a box here, and a box here, etc., etc. And as you can see, these boxes are not optimal because they do not cover everything. But the smaller you make these boxes, so the smaller you make them, the better they fit under the curve of the graph. Now I know this is kind of an ugly drawing, but I hope it gets the point across. So you fit these boxes under the curve basically. And so in our Python code, this n is the number of boxes that you have. So in this case we fit 20 boxes under a certain function. Now let's, for example, use the following function. So let's define lambda x. So that is how you define the function again when it takes x as its variable. And this would be cosine x to the power 2. So for example, this function. And then if we want to take the integral in Python, what we can do is we can say dx is b minus a, where b and a are the intervals, so it's from 0 to 1, divided by n. So basically what you do with this step is for the whole range, so basically for the whole interval, so b minus a, you divide it by the number of boxes. So yeah, how can I say this differently? How can I say? Or maybe I can draw it again. Hang on. So I'm looking at this picture right now, but it's not in the slide. So that's. Can I move it here? Can I somehow move it here? Oh, hey, I can. Well, no, I can't. It's Arjan, help.
Oh, well, what's the problem? What do you want to do?
I wanted to show them this picture.
Just keep dragging it. Just keep dragging. Keep dragging.
Oh, okay. Yes, computers, guys. I know how to work with them. So basically, what this code does is that for the interval from 0 to 2 in this case, so this picture is different from this code, but it basically shows the idea of what is happening. So from the interval from b to a, so you take this whole length, so in this case that would be 2, in this code it would be 1, divided by n, so for example divided by 20, so you take 1/20, so this is basically the length of one of the boxes. And then you can say, so x range is just defining the range in which you will have it, so in this case it's from 0 to 1 with steps of n. And so what we can then do is we can say, okay, so the result of this approximation of the integral is the sum, and then we take, so this is, yeah, it's a list basically, or a set, and we can say, okay, so for every length of one of the boxes, so that will be dx, times the function, so the outcome of this function, we make like a box, right? So we take this length of this box here, and then with the height of the function, so that will be your fx, for every x in this range, so for x range from 1 to 0, or in this case that will be 1 to 2. So we take the length of the box times the height of the box, we do that for every box, and then we sum those boxes. And that is basically the area of all these boxes together, so approximation of the area under the curve. And the more boxes you have, the smaller these boxes become, and the better they are at approximating the area under the curve, and thus approximating the integral. So we can then print, well, the approximation value of the integral is, and then this is a way to format it, but you can also just say the approximation value of the integral is, and then plus result, string of result, right? You can also use the format notation, it's fine. So your result will be the sum of all these boxes, so it will be the approximation of your integral. So that is basically how taking an integral in Python works. This could be asked on your exam, I think. So this is, I think, a good one to study. And well, I think that is everything I had. Let me put this one back here. Alright. Oh. Ooh. Okay, hang on. Yeah, right, I fixed it. Nice. Okay, cool. So, let's see. So that is the Python code. Yeah, so that was it for me. I don't know, Arjan, if you want to take over and explain the last final question.
Sure.
That was asked a while back.
Yeah. You could also do the integration if you like, otherwise it will switch twice.
Oh yeah, sure, you can also do the integration that she does. Maybe someone else explaining it again will give a fresh view.
So the person with the question about the definition of the derivation for x squared, is the person still here? I mean, I can still do it, but if no one else is still interested in it, then of course it will be a little bit weird. So let me know. But otherwise I can go over the integration if the... I don't know where the question, when it was asked.
Yeah, so they put it in the chat again, Arjan.
Okay, yeah, now integrate the cosine x e to the power x if the definition question is not here. So what I want to integrate is the cosine of x times e to the power of x dx, right? Do we want to still that question? Okay, then actually let me do that derivation first because that's quicker, and then we can go to the integration part. So if you want to derive this into this for definition of the derivation, how you do this is you have of course the limit of delta x to 0. What we fill in here is our function of x plus this delta x minus f of x minus delta x divided by 2 times delta x. Yeah, that's what I'm doing right now. So what we are going to do here is fill in, of course, f of x because we don't know what f of x is. So what we get is the limit of delta x approaching to 0 of x plus delta x squared minus x minus delta x squared divided by 2 times delta of x. Well, what will this be? Let's work out the brackets that we can find out. So we have the limit again, delta x approaching 0. Working out the brackets, we get x squared plus, of course, delta x times x, and then again delta x times x. So we get 2 times x times delta of x plus delta of x. And this, of course, yeah, squared. Minus x squared. Let's actually work out the brackets, but not the minus in front of it yet. So we get x squared minus 2 delta x, well, 2x delta x plus delta x squared. So this is if we just work out the brackets, nothing fancy yet. Then again we have the limit of delta x. Now we're going to work out the brackets and see if stuff actually falls away against each other. let me see, we have x squared here, and it will be a minus x squared, so that will be 0. We have a plus 2x dx there, and we have a minus 2 dx here, so there will be a plus 4x dx, so we get 4x times delta x, and here we have plus delta x squared minus plus delta x squared, so that will also be 0, divided by 2 times delta x. So we see that a lot of terms actually cancel each other out. Well, now it is fairly easy to see that if we take the limit from delta x to 0, before we do that even, we can divide by 2 and by delta x, so we are literally left with 2x. And of course, actually, I mean, if we want to be technically correct, we have the limit of delta x to 0 of 2x, but 2x is nothing with delta x left anymore, so this is the same as 2x. And thus proven that if we derive x squared with the definition of derivation, we get to 2x. Did that answer your question? I hope so. And if not, let me know. Okay, great. Then let's go to the integration. And for that we need to use integration by parts. So what do we have? We have the integral of cosine of x times e to the power x dx. And we want to integrate this. And we see that we have two functions multiplied with each other. So if we have two functions multiplied with each other, we are going to use the integration by parts. So we have our functions. Normally what you would do with the integration by part is checking which function is close to being eliminated. So for example, if you have an x squared or something inside of your product, you want to be able to derive that one so it goes away actually in your formula. But right now we have a cosine, which will always turn to a sine, into a cosine, to a sine and cosine, and your e to the power x, which will always stay e to the power of x. So this is a little bit tricky, but we will get to an answer, because the first thing we want to do is we're going to integrate one, and the other one we're just going to leave be, and then we fill in, of course, the derivative one. So which one we're going to choose? Let's actually say we're going to integrate e of x. So this is our derived version, and this is our normal function. So we get e of x, like we have integrated it, because it's still the same, times cosine of x, minus the integral of e of x times the the derivation of cosine of x, which is the minus sine of x dx. Yeah, this is just the integration by parts rule applied. If things are unclear so far, just let me know, and if not, I'll continue. So we can actually work out, of course, this minus sign, so we actually get e to the power of x times cosine of x plus the integral of e to x times sine of x dx. What as you can see is we are not actually progressing much, so we probably have to do this one again with integration by parts. So let's do that. The integral of e to the power of x times sine of x dx is equal to, well, if we say the same thing, let's say that this is the derivative function, then we're going to integrate that one, and it's still the same, times the sine of x normally, minus the integral of e to the power of x times the derivation of sine of x, which is cosine of x dx. Yeah? Now, you might still think, well, how is this helping us in any way? Well, we have actually just cycled back to what we had originally. Well, this is actually very nice, because right now we can fill it in back into our original function, what we have right here. So let's do that. Hopefully it will all fit. We'll see. cosine of x times e of x dx is equal to e of x times cosine of x plus, and now we get to this part here, e of x times the sine of x minus the integral of e to the power of x times the cosine of x dx. Now, as you can see, we have one thing we have twice. We have cosine times e of x dx here. Let's do another color, purple. We have it right here, but we also have it here. So what we can actually do is we can get it to the other side of our equation, which will give us the following. 2 times the integral of cosine of x times e of x dx is equal to e of x times cosine of x plus e of x times sine of x. Now, we can divide, of course, left and right side by 2, and we can take out the e for now. We can take it outside of the brackets to make it even a little bit easier. So what do we get? We get that the integral of the cosine of x times e to the power of x dx is equal to e to the power of x. Let's also say times a half, because if we divide by 2 is the same as multiplying with a half. You can even write it at the front of cosine of x plus the sine of x. And we're done with integrating. So if you have, this is like an indefinite integral because there are no boundaries, but if you have a definite integral with boundaries, then you can just, of course, fill it in here for your boundaries. But this is how you integrate a function by parts, where it looks like neither of both functions are actually converging to a number or helping you solve the integral by parts. And in this way, if you can create what you had originally, you can actually get it to the other side, and in that way solve your integration. Yes, no problem. I hope it was all clear and you learned something from it. If there are no other questions for chat, then the stream will soon be over, and you can still ask questions on Discord, in the Cognac Discord, or the Calculus Discord, for what you prefer, but I think the Cognac Discord is better because more people are in the Cognac Discord. So yeah, that's it for today. Do any of you still want to say something?
No, I think you've covered it all.
Yeah? So don't forget to hit that like button, subscribe, and ring that bell for notifications. You know it. Yeah. And thank you for the study committee to set this all up and give you this workshop. I understand that the course can be very frustrating indeed for first years, and Luca is not helping at all. He's just being a real pain in the ass. Yeah, we understand. It was last year. Last year was way less. He's become more of a dictator.
But it's also because like it's online now, so everything is already more confused.
Yeah, so if you really hate this, please fill out the course evaluation and just flame him completely, because then actually the course can change. Otherwise, it's like there's no proof. Okay, so have a nice evening, and if you have questions, just let me know. And good luck with your exam.
Good luck, guys.
Good luck.
Bye.
Bye.